Yes, that could perfectly understand this. It's like to bring. Okay, guys, if I can have everyone have their phones up here, since I'm missing. Okay, today we're starting our new units, but we're just going to be doing a quiz on this unit. It's really just related rates. That's really the main topic. Linear approximation is a minor topic, but it's something that we're going to know. You're going to find it pretty straightforward. Just have to keep in mind it's something that you already know how to do. You just have to adjust to the wording that they're giving you. And in L'Hopital's rule, we're going back to limits for a little bit, but it's good because it's a much faster process than the limits that we were doing at the beginning of the semester. But now it's involving derivatives to find limits. But ultimately, the bulk of our topic is with related rates, which is implicit differentiation with time as the independent variable. So as a kind of a word problem feel to it. If we can get done with 4.2 today, we can do a little bit of intro into related rates. We're just going to have a quiz over this this unit. We can start our quiz review on Friday, and then I'll give you a new calendar quiz be sometime next week. So in your packet, let's turn to page 1. A tangent line of a function f of x at x equals a can give you an approximate value of f of x for points close to x equals a. So we haven't quite talked about this in detail yet, but we're going to talk about it after this unit, is the idea of concavity. But right now, just know that concave up and concave down just means the curvature of the graph. So imagine concave up is a graph shaped like a parabola opening up. And then concave down is a graph that is shaped, again, like a parabola, but opening down. Right. So let's say we have a tangent line. And it skims the surface of the line. And it shares the same point. It shares the same slope as that curve. Now, let's say we wanted to find f of 6. So this is y of x, that's the line. F of x is the curve. So do we agree that f of 6 and y of 6 will be the same y value? Yes. Yes. Yeah. The curve has the same point as the line because the line is tangent to that curve. Now the question is, if I were to do a decimal value, y of 6.1 versus f of 6.1, will they be the same value? No, right? It's in the but we can say that y of 6.1 is an approximation of f of 6.1. Obviously, the closer that we are to our tangent point, the better our approximation is. We don't have to worry about how accurate our approximation is, but let me ask you this then. Is the approximation that we get going to be higher or lower than the actual value? The approximation. The approximation is using the line. So how is y of 6.1 going to compare with f of 6.1? Which one is higher? The f, right? So the graph is going to be higher. What if the tangent line was elsewhere? What if it was over here or over here? Is the tangent line always going to be below the curve in terms of approximation? It is. Okay. So that's the key thing. That's really the big idea here with this graph is that if I ever have a concave up graph, my tangent line is always going to underestimate or under approximate my function value. What if I had a graph that is concave down? Yeah, then my tangent line is always going to sit above the curve, and my tangent line is always going to give me an approximation that is higher than the actual value. And this is not something that we have to memorize, because if you just sketch your graph, you should always be able to see, okay, well, I can see my graph is higher, so therefore my graph is going to be my line. Sorry, I can see that my line is lower, so then the graph, so the line must be underestimating. And then I see that my line here is above the graph, concave down graph, so my line must be over approximating. Okay. All right, does that concept make sense?
Basically, it overestimates like the tangent lines to be higher than
the actual point on the curve.
And when it's underestimates the opposite, the tangent line's lower.
Tangent line's lower, exactly. Yeah. But our focus today is finding that tangent line equation and then plugging the decimal and then finding an approximation. And if the problem says, hey, this graph is concave up, then you can say, okay, my approximation is going to be under the actual value. We don't have to worry about how accurate it is. We just have to say whether it's underestimating or overestimating. But they always have to tell you, at least we'll give you some way of finding out whether the curve is concave up or concave down.
Are we usually have to draw a graph for these problems?
No, but I think drawing the graph can help remind you, okay, this is over approximating, this is under approximating. But we don't have to draw the graph yet, not this unit. Okay. Let's look at number 1. Function is concave up on its domain, and f of 4 goes at 5, f prime of 4 equals 3. What is the estimate of f of 3.8 using local linear approximation for f at x equals 4? Now, before we do anything with approximation, we have to build our tangent line equation. So what information do I need to build my tangent line equation? Let's remind ourselves that.
Well, it's underestimate, right?
Eventually, we're going to deal with that. But if I just ask you from previous unit that we've learned, how do we find the tangent line equation? What information do we need? Slope and a point. So we need a point and slope. And then once you do that, then point slope form, right? All right, you already know how to do this. So let's just gather that information. So what's my point? What point do they give us?
4, 5.
4, 5. Now, if they don't give you the actual y value, then they will have to give you a function and you'll plug in 4 to get the y value, right? But this one, it's nice, it gives you that order pair directly. Okay. And what's the slope? 3. And if the slope was not given to you, then you would find f prime, then plug 4 into the derivative, get the number, and that's your slope. Okay, good. Now, what's my tangent line equation?
Y minus 5 equals 3 times x minus 4.
Good. All right, nothing new yet, right? Nothing new yet. I'm going to do one thing to kind of help us with the next step. Let's just move that 5 over to get that y by itself. I think this will help us with the next step. What would that look like if I were to get y by itself?
Y equals 3 times x minus 4 plus 5.
Okay. All right, up to this point, nothing is new, right? We know how to do this. Now you're going to find this next step. Hopefully this is easy for you. What is the estimate of f of 3.8? All we do, now that we have our tangent line equation, We're just plugging the decimal into the tangent line equation to get that approximation. I know this is not the graph, I just want to kind of give you some visual connection here. So all we're doing is we're taking the decimal that they give us, and we're just inserting it in for x. That is all. So y of 30.8, we know it's not going to be an exact value, but it's going to be an approximation using a line, and that's why it's called a linear approximation. We're using a tangent line to approximate some decimal they want us to approximate. Okay, you'll get to use your calculator, but I'm going to do this for us right now. It'll give us 4.4.
What was like, I'm saying, what was the estimate for like F prime derivatives?
I won't ask you that. And if I were to ask you that, then I'll have to give you more information. I would have to give you F prime of 4 and F double prime of 4. Make the tangent line for the derivative function. Plug in, but. All right, so the only thing new is we're plugging a decimal into the tangent line equation that you already know how to do. Okay? That's all it is. That's linear approximation. It sounds complicated, but really it's just you're plugging a decimal into your linear equation. Any questions? Okay, so is this an underestimate or overestimate? Well, we know our graph is concave up. So where's our line going to sit? Above or below?
Below.
Below. So therefore, my tangent line is going to underestimate. Okay, and then the only justification we have to provide is my function is concave up. My linear approximation is going to be an underestimation, under approximation. Okay, number 2, we have to do a little bit more work because we have to find the information. It's not just given to us. We got to actually use the function. But same process, right? Find your order pair, find your slope. Is everybody okay with number 1? Here's number 2. So our function is given. The graph is concave down. We'll worry about that later. But we have x equals 1 and our function, find the tangent line at x equals 1. So how do we find the point?
Plug in one to the equation.
And then how do I find slope?
Power rule.
Take the derivative, yeah, power rule, and then plug 1 into the derivative, yeah.
It doesn't matter like the order of the degrees, right?
What do you mean?
Like
Yeah, it doesn't matter, right? You can start with a lower degree and the same thing. All right, f prime of 1. Okay, we have our tangent line, or we have enough information for our tangent line equation. Take our order pair, take our slope, point slope form. Oh, sorry, thanks. Okay, so f prime, we plug in the derivative to get our slope. So we have everything that we need to build our tangent line equation. Take our order pair, take our slope, point slope form. And then part B, we have the one final step ahead of us, and that is as easy as just placing that 1.1 in for x. Now, I would add that 1 over to the right side, get that y by itself. It just saves a step. Eventually, that 1 has to come over anyways.
Even for your answer, you can bring the 1 over.
Yeah. Let's get that y by itself. I want to get my approximation for y, so I'm going to make that -1 a +1 on the other side, and then plug in the 1.1. Okay, underestimate or overestimate? Because concave down, right? Concave down, my tangent line is always going to sit above the curve. My tangent line is going to produce an over approximation.
You know if it's concave down or up by just looking at the points.
Well, I think the problem tells you, the problem has to tell you whether it's concave up or concave down. So here, concave down.
So that answer will be pretty simple. So it's not,
I'm sorry?
that answer will be pretty simple. It's time and C. Like,
Yeah, yeah. As long as you know what that relationship is. All right, everybody okay? 1 or 2? 1 and 2. Okay, number 3, it feels more complicated, but it's actually not. It says consider the differential equation. Now that word, I've seen that before. So differential equation, all that means is it's a derivative equation. That's all it is. Differential equation is derivative equation. We're going to use this phrase a lot more second semester when we talk about solving a differential equation. But right now, just know it's some slope formula. We don't have to derive it. It's already given to us. So it does the same thing as other derivatives. You give it enough information. In return, it'll give you a number, and that number is going to be the slope of whatever the original graph is. Let y equals f of x be the particular solution to the differential equation. So we have some function that we don't know the full detail of, but they do give us enough information. They tell us our order pair is 2, 0. So write an equation for the line tangent to the graph at the point 2, 0. So if I have the order pair, what can I do to find the slope? Into the derivative, right? So my derivative is my differential equation is my derivative. So whenever we want to plug in order pair into something that requires both x and y, we use this notation here, dy dx with a vertical bar 2, 0, because it requires more than just an x, right? Usually it's just the x that we need, but this derivative needs more information. So we need to give it both the 2 and the 0. Okay, I know we were taught a little bit about exponentials in the beginning, but you guys remember e to the 0, or basically anything raised to the 0 power is what? 1. Yeah. So that's just not going to matter to us here. So 2 times 4 is 8. 8 minus 10 is -2.
is there ever a point where E is going to matter? Like, it's going to be like,
Yeah, we're gonna devote a unit just for exponentials and logs, and we'll do that after the next unit. Probably November, early November. Yeah, so we'll talk about, we'll go back and review exponentials a bit more. Okay, so what is this? This is the what? Slope. Okay, so we have our order pair, we have our slope. Let's build our tangent line equation. And then what's the final step? Plug 2.2 in for x, yeah. So linear approximation. If you don't remember the steps for in the future, just think about those two words, right? Linear approximation. Create the line, create your tangent line equation, and then plug in the approximation is you take that decimal, you plug into the line. Right, your homework is pages 2 and 3. I'll do a couple of these and then you guys can finish it for homework. I do want to see if I can start a little bit on 4.3, but I'll just do one of each page and then you'll have a model to kind of follow through. But it's basically what we've been doing the first page. Okay, says use the given information. Sorry, the homework says 35 to 38 all. You're just going to say pages 2 to 3 in the packet. And I'll put this back up again. We're just doing, I'll just check the 2 pages tomorrow. This should be quick. All right, so use the given information in linear approximation to approximate the value of the function at C. So there's your point, there's your slope, and there's your decimal. So find the tangent line equation. You have your order pair, you have your slope. Point slope form. Let's just move that 8 over to make it a little bit cleaner. And then the final step. Plug in 2.06, so y.
Basically, the C value is just a number of some plugged in.
Yeah, the C value is your decimal value. And usually your decimal value is going to be pretty close to your point of tangency because, otherwise, if it's too far away, it doesn't really have a much purpose because the line is going to be probably too far away from the curve. You want the line to be relatively close to the curve in order for it to be some sort of a decent approximation. You guys get 7.82. Okay, so 2, 3, and 4 are the same process. Are we okay with 1? Okay, let's go to page 3. I'll do one of these with you. Okay, so linear approximation steps. This one says find the tangent line using the nearest integer. So we're not going to play with the decimal yet. We just want to find an integer that's close by. So what x value can we choose? 1. So we'll choose at x equals 1. Okay, I'll skip number 1. I think this is pretty straightforward, right? You plug in 1, plug in, find the derivative, then plug in the 1, get the tangent line equation, and okay. Number 6, we still want to use what?
1.
At x equals 1. But to find the derivative, this would require what? Quotient. Okay, so I'll leave that for you to do later. I'll do the third one with you. Okay, so given cube root of 3x plus 2, use linear approximation to approximate f2.1.
At x equals 2.
Yeah, let's use x equals 2. And the decimal value ignore the decimal value until the end, right? You're going to build your tangent line equation before you do anything with the decimal. Okay, but we have a nice integer to play with here. What can we do first? Let's do the pre-calculus step. What's easy? What's something easy that
Oh, like 1/3.
yeah, to the 1/3, and then what information do we need? How about that? What information do we need to build the tangent line equation?
Yeah.
Plug in the 2, right? So yeah, it doesn't matter if you decide to find the derivative first. I just figured, well, we have this in front of us. Let's just go ahead and take care of that step. Three times 2 is 6. 6 plus 2 is 8. Square root of 8 is not going to clean up. I mean, we could make it 2√2, but that's fine. Oh, I'm sorry, 1/3, right? Not 1/2. This actually will work out. What's the cube root of 8? 2. This one does work out. Okay, good. Now we can build the derivative. And to build the derivative here, what rule do we need? Chain rule, right? You see that outside-inside portion. Outside's derivative, bring down the 1/3, keep the parentheses, subtract 1 from the exponent, then multiply by the inside function's derivative. Let me do some cleanup here. 3 and 3 cancels out. I'm going to push that 3x plus 2 to the bottom. All right, a bit more work than previously, right? Now that I have my derivative, I can find my what? Slope, plug in what? 2. Okay, 1/8 to the 2/3. You can plug this in the calculator. An easy way to do this by hand is don't square it first, because that makes it a little bit harder. Do the cube root first. What's the cube root of 8? 2, and then 2 squared is 4. So that makes it a little bit easier. Now that 4 is in the denominator, so my slope is 1/4. My order pair is 2, 2. Point slope form, and then we can work in that decimal.
So it's like what we've been doing, but like taking it a step further, basically.
That's right. One step further, and that's just plugging that decimal. Right? So this feels like review. We just now have a name for this process, linear approximation.
How do you get 1/4 from like 1/8?
Right. So a to the 2/3 is the same thing as 8 squared to 1/3. But I can flip flop these. I don't have to do it in a certain order. So I can make this 8 to the 1/3 and then square it.
Oh.
And then what's 8 to the 1/3?
It's 2.
It's 2, then 2 squared is.
It's 4. And 64 cubed also. 64.
Right, but the reason that, I mean, obviously with the calculator, you get the same thing, but this, creating a larger number, sometimes it makes it a little bit harder to work it down, right? Imagine this is like 8 to the 4/3. We would prefer not to raise to the 4th, we would prefer to get it down to the 1/3 before raising it to the 4th power. So that's the strategy there, but we feel like we gotta do the numerator first, but we don't. I mean, sometimes the denominator, especially without a calculator, will just feel a lot more manageable to do.
When you use a calculator in a split,
This one, I'll give you a calculator for this quiz. Okay, are we good with linear approximation? Okay, so page 2 and 3 will be your homework. I do want to take about 10 minutes or so to start the next unit, because the bulk of this unit is what our focus will mainly be. This is what's makes it requiring us to do more work here. So related rates are problems involving rates of change, but instead of variable x, we're doing this with respect to time, okay? With respect to time t. So this is also an application of implicit differentiation. We find the derivative of variables with respect to time t. Now, let me just step to the side and just do a problem here. Let's say I had y is equal to 2x plus 4. If I ask you to find the derivative, y becomes what? Y prime, okay, but yeah, I want to use dy dx just so we kind of see that's a connection with this unit. Equals, and then 2x becomes what? 2. Now, technically, there's a dx over dx, right? But we said that it washes out, and then the 4 goes to a 0, right? So dy dx equals 2. Now, obviously, that goes 0, so just the slope is just 2. Now, imagine us doing the same thing, but instead of d over dx is now d over dt. That's what we're doing here. So y becomes now dy dt. Now we're finding the derivative with a new independent variable, time. And then 2 dx over dx will become dx over dt. Now this we have to keep because this is not just going to wash out, right? It's not dx over dx. So calculus-wise, the only thing we have to adjust is instead of d over dx is now d over dt. Okay. And I'll talk about what it means for our problem. But I think what you're going to discover is that your calculus this unit is going to be easy. It's the setup that's going to require more work because it's all just going to be power rule. But it's the setup in terms of the word problem makes it a little bit more challenging. So these are the steps we're going to take. I'm not going to do these in the order that's presented. Sometimes I like to gather information in a different order, but ultimately it's the same idea with word problems. You always want to identify what you're given. You want to identify what you're trying to find. In this case, we always want to create an algebraic or geometric equation before, so that we can actually have something to build the derivative from. Differentiate equation, that just means find the derivative. And then in the end, we're just going to solve for the variable that the problem asks us to solve. Okay, I'm going to refer back to these notes. I'm going to spiral back to this, but remember that when an item is bigger, your rate is positive. Remember that the item is smaller, then the rate is negative, regardless of direction. Okay, and that's something that we have to get used to. We typically associate direction with a certain sign, right? Positive is right, vertical going up is positive, but direction is not going to matter. Okay, all right. Let's see if I can squeeze in 1 or 2 examples. It says the size of a square are increasing at a rate of 5 centimeters per minute. How fast is the area increasing when the sides measure 15 centimeters in length? So we're asking about area. Okay. We're asking about how fast the area. Now we're talking about the area of what shape here? Square. Okay, so that is how we're going to build out our equation. So area of a square, remember, what's the formula for area of a square?
Length times width.
Length times width, but the length and width are what? They're equal, so length times length, or width times width. I'm gonna use x to be the length side, and it's just length times width, x times x, because a square has equal dimensions. Now, I like to do this. I like to just go ahead and find the derivative, because then I have all the variables in front of me and I can start to kind of decide, okay, I have this information, I don't have this. So we're going to find the derivative of this, but now remember, every time we find the derivative, we're going to have to find that variable's derivative and then attach a d over dt for that variable. Okay, so I want you to see if you can figure out what that means. If I find the derivative of a, what's the derivative of a? Well, let's just focus on the a here. What does the a become? A prime. Now, let me ask you, if I ask you for y, what's y's derivative? 1, right? Because the first power, you would say 1 dy over dx. So therefore, a becomes what? 1. It's not d. It's dA over dt. That's going to be your pattern, okay? Because I'm finding the derivative of my variable a with respect to time t. Okay? So that's going to be the pattern for all of these. Okay, time is going to be our underlying variable that's going to influence everything. Okay, what do you think x squared is going to turn into? 2x. Now it's also going to have its own derivative variable, dx over dt. That's the pattern. Every variable is going to have it's going to show up in that numerator of the derivative, and then denominator is going to be a d over dt.
So it's not as wise anymore. Now it's
No longer dy dx, because I mean it may still be dy over dt, but it's no longer over dx because x is not our independent variable now. Time is independent variable.
We'll tell you one like the exam if it's like turned to x or like the time.
I think we have to kind of figure that out. Basically, if you see something where there's like a time component in the problem, it's usually going to be related rates. Okay, so the size of a square are increasing at a rate of 5 centimeters per minute. Now, what variable do you think is going to hold this? What is going to hold this information?
It's the derivative.
Well, let's not. Yeah, derivative. Size of a square. What variable do we use to hold size of a square? X, right? But it's not just x. It's a rate. So guess what this is talking about?
It's rate change.
So which variable is that talking about? Of the variables that we see in front of us, which variable is this referring to? Dx over dt. Okay, because you see size of a square, that's x. You see a time component, so it must be dt involved. So I'm going to step to the side here and say dx dt is equal to 5. Now, is my dx dt getting larger or getting smaller? Larger because of the word what? Increasing. So anytime we see a rate, we're going to have to decide is it positive or is it negative. Okay, if you see the word increasing, positive. If you see the word decreasing, that's going to be negative. Okay. How fast is the area increasing? What are we looking for? Which variable in front of you do you think would be best suited for this, what we're looking for there? D what? dA over dt, right? Area, that's obviously it's either one of these two variables, but you see the word increasing. So anytime you see a rate involved with a variable, it can't just be a static value. It has to be a moving value, right? So dA dt is the unknown. When the size measure 15 centimeters in length. What's that 15 referring to? X, yeah. So if you're ever having trouble deciding, wait, which variable is going to go with what? If you see anything that has a time component, or we see the word increase, decrease, or changing, if it's
anything referring, those words referring to a variable, then you know it has to be some sort of a d over dt. It can't be a static value that is not changing at all. Okay, so I think we have enough information. We're looking for d8 dt. We have x, we have dx dt, so we can just insert everything back into our equation, right? So d8 dt equals 2 times times 5. So 10 times 5 is 150. Now, our units, you see how there are two variables here? We need units with numerator and denominator. What's the area unit? Centimeters squared, right? Area is a two-dimensional unit. So centimeters squared. And then there's a time component here. So
Miss.
per minute. Yeah. So if you're ever struggling with your units, look at the variables involved. Area, that's a two-dimensional unit. Time, it's minute, so just put them over each other, centimeters squared per minute. So this tells us that the area of the square at this moment in time is increasing at a rate of 150 centimeters squares per minute.
So that slash means the same thing as per.
Per, yeah. All right, let's do one more here. If we don't finish it, it's okay. At least we have a head start. A 25-foot ladder is leaning against a vertical wall. The bottom of the ladder is being pulled horizontally away from the wall. How fast is the top of the ladder moving? And in what direction when the bottom ladder is 50 feet from the wall? Let's draw the picture here. There's my ladder. Ladder is leaning up against the wall. It's getting pulled away from the wall. So I want you to imagine the path of that and the shape changing as that ladder gets pulled away. Okay, what shape do you see in front of you here? Triangle. So we're talking about something involving a right triangle. Okay. I'm going to go ahead and label my variables here. I'm going to let my horizontal be my x, vertical be my y, and then my hypotenuse, where that ladder is, be my z. Okay, this is going to be a popular type of setup where what equation can we use that relates to the real size of a right triangle? Pythagorean theorem, right? A squared plus b squared equals c squared. I'm going to use x, y, and z just to, but it's the same idea. Right? I use x and y because I think we typically associate x with horizontal, y with vertical, so it just feels more straightforward. Now we're going to find the derivative. Every variable, we're going to go through power rule, but as soon as we apply power rule, we're going to attach a derivative in terms of time for that variable. Okay, so see if we can remember that process from above. X squared becomes what? 2x, and then we need to attach what?
Yeah.
Good. That's it. Same pattern over and over again. Y squared.
2y or dy.
Yeah. And then z squared is
2z over z.
2z.
pz.
Yeah. So let me talk about what these variables mean. X and y and z. These mean what is the length of each of my sides of a triangle at a moment in time. Dx dt means how fast is this length changing. Dy dt, how fast is this length changing? And dz dt is asking how fast is this length changing.
Oh, are we going to involve triggers? You can say a triangle.
Eventually, but I'm going to save the trig portion for the last unit. I'm going to group all the trig unit for later, but we'll definitely revisit this problem when we get to our trig unit. But right now, how many variables do you see in front of you?
Or 6.
6. Okay, so I'm going to put those down. Okay, let's see if we can go back to our problem, and we'll just try to fill in as many variables as we can. Our hope is that there's only one left over a variable that we need to solve for, and then we can plug everything in. 5 out of the 6 are plugged in. We can solve for the 6th one, the missing one. Okay, a 25-foot ladder is leaning against a vertical wall. Where is that 25 going to go? Z, okay. The bottom of the ladder is being pulled horizontally away at a rate of 3 feet per second. What do you think is going to hold this information? Something over dt. Which one is it? Dx, okay. How do you know it's dx over dt?
It's like horizontal.
Horizontal, yep, good, horizontal, right? You visualize it must be involving the x here. Now, is this length getting longer or shorter?
It's getting longer.
Longer, so this rate is going to be positive. Okay. Now, I purposely drew it this way. You see how it's going left? I want to just show that the direction has no bearing on the problem. Sometimes we associate left with negative, so don't worry about the direction. Look at what is happening to that value. If you can imagine that value growing, you want that rate to be positive. So you always have to kind of visualize can I imagine this problem in motion? And then once you imagine it in motion, you can decide, okay, that's getting longer, that's getting shorter, and that will help you dictate what your sign is going to be. How fast is the top of the ladder moving? What are we looking for?
Like it's going to y, dy dt.
Good, dy dt, right? We know it has to involve the y, but you see the word fast, moving, right? So all those movement words are telling you it's not just a static value, it's a rate.
Negative 15, right? It's like
Well, that's the unknown, okay? But I think you get the right idea. You're expecting dy dt to be negative because why?
because it's like decrease.
Decreasing, not because it's going down, right? But because that vertical distance is decreasing. Yeah. We don't know what that value is, but it says when the bottom of the ladder is 15 feet from the wall. What is that? That's your x. That's your x. Now, we said we wanted 5 out of the 6, but we have 3. We have the unknown. But let's see what we can do to gather this without just by looking at the problem again. Now, if I know my x is 15 and my z is 25, can I figure out what y is at that moment?
Yeah, that's
I can.
great.
That's just what Pythagorean theorem, right? A squared plus b squared equals c squared. You can use your calculator, but also if you recognize this as a variation of a 3, 4, 5 right triangle, then 15. 20, yeah. But if you don't know it, it's okay. You can just do 15 squared plus y squared equals 25 squared. Subtract 15 squared, take the square root, you'll get 400 squared, 400 is 20. Good. Now, dz dt.
Divided by 5.
Well, let's think about this, right? Z is the length of my ladder. What is the rate of change of my ladder? How fast is this length changing over time? Well, let me ask you this. The ladder is 25 foot long.
The length of the ladder doesn't change.
Good. It doesn't change, right? It's going to be 25 foot long at the beginning of the problem. By the time it hits the ground, it's still going to be 25 foot long. So my rate of change is going to be what? 0. It never changes, right? That length is always going to remain 25. Okay. So that's the hard part. The rest, we're just plugging into the derivative equation, and then we're solving for dy dt. Okay, we'll save that for tomorrow. Your homework is page 2 and 3. Come get your phones.
Your final answer going to be dy dt.
Yeah, you're solving for dy dt.
This one, like,
You're seeing that.
these are 5 over here. Do you want me to like
That's fine.
simplify it more?
No, this is good. That's good.
Make sure you study the one of dy dx.
Just your
Implicit. Make sure you study all that. Like, there's a lot of implicit stuff.
Okay, thanks.
Is too calm. Recovery be for like the last test.
I gotta create it first.
Okay.
And then once I get it back to you, we can figure out.
Okay.
if we need to.
Y'all went on Saturday?
Yeah. Did you get my text over the weekend? No, okay.
See.
Okay.
When's good?
When's good for you?
Yeah, Saturday is when.
Yeah.
I saw that.
So Mondays.
Dude, that's not really good.
Babe, take it because I have a just wait. But tomorrow.
The Bills smelled like there's some, we got overshot by the 17 points. We played them this week. I was kind of scared.